Hi everyone. I actually wanted to share how we would work through a piecewise function. I think that some of the videos that we've had are helpful, but I really wanted to break this down. I feel like it's going to be even more helpful to hear me talk through the steps that I personally would take for graphing a piecewise function, and I hope that you like this as well. So, for instance, with this particular example that we have, I want you to consider that we actually have sets of boundaries, right? So we have three different equations. Your first equation is that y is equal to -4. This particular equation only exists when x is less than or equal to -3. So that right there exists as one of our boundaries. So x is less than or equal to -3, which means I'm actually just going to go ahead and draw like this dotted line. Technically, you could do the dotted line on your papers if you're doing this in class or on a test. You don't need the dotted line, but I like to kind of see it for visual purposes. My second equation is going to be y is equal to x squared minus 1. This particular graph only exists between -3 and 2. So again, we have another boundary, and that is +2. So I'm going to go ahead and draw my dotted line here. So no big deal. It doesn't have to be super, super nice. My final graph is the equation y is equal to -2x plus 4. And we see that that only exists when x is greater than or equal to 2. Okay, now the next thing that I think is going to be incredibly helpful is you should think about what does it look like, right? So for instance, when you see the equation y is equal to -4, my hope is that you see this equation and you think horizontal line, right? This is a linear equation. We know there's no x coordinate, no x variable, excuse me, in the equation itself. So this is a horizontal line. Now, let's move to the second one. Here we have y is equal to x squared minus 1. We have used the parent function, which is y equals x squared. We know what this looks like. We know what a quadratic functions look like. It's a parabola, right? It's that u. So if we were going to graph this, it's got to look something like a u. That should be in there. And then last but not least, we have y is equal to -2x plus 4. Well, that's slope-intercept form for the equation of a line. And notice that our slope is negative, so it's going to look something like this, which I think is going to be helpful again. So we know that our three shapes, what they're supposed to look like on this graph, and now we just have to actually make that happen. Now, the most effective way to make this happen is to graph by plotting points. That would be my perspective. That is something that I think would be incredibly easy. We can use this every time and just knock these out of the park. With that being said, I'm going to actually start this first equation, y is equal to -4, even though I know it's horizontal. And I'm saying that this exists when x is less than -3. So my very first point that I'm going to use is the fact that x is -3, and we know that y is -4. So that's going to be here, -3, -4. And notice because it's x is less than or equal to -3, that it's going to be a solid circle here. So we're filling this in to make sure that we are including that endpoint on the boundary. And then of course, our function, y equals -4, exists everywhere x is less than -3. So I could pick any x value less than -3, we'll go with -6. So when x is -6, y is still going to be -4. But we know that because it's a horizontal line. So we have x is -6, y is -4. There's my second point. It's never going to be an open point on the actual line in the region because you're only open or closed on the boundaries. Okay, that's the whole point. So I'm going to go ahead and use my line tool, and I'm going to connect this and make this go left, and bam, sorry, that shifted up a tiny bit, but that's my horizontal line. It's as good as it gets right now. Okay, let's do the same thing with our parabola. We have two boundary points, -3 and 2, but this is a u. So I want to make sure that I'm plotting this correctly. One of the things we could think about is because we already did transformations and we know what y is equal to x squared looks like, we can say, well, it's y equals x squared, but we shift it down 1 unit. So remember, that y equals x squared looks like this. Sorry, it goes through, I can't even make it go through. It goes through the origin at 0, 0. So if you take y is equal to x squared and then you vertically shift this down 1 unit, that means we're going through the point 0, -1. That's actually our vertex, right? It's the lowest point. So 0, -1 is here, which is actually pretty cool and it helps us out. But we're still going to plot points and make this a full picture. Let's start with our left boundary point, which is -3. So if I plug in -3 here, I want you to think of this as, let's get rid of this. So we have -3, whoop, quantity squared minus 1. That's a +9 minus 1, which is 8. Now, on this endpoint, we see that it has to be an open circle. On the boundaries, open or closed. That's where we're actually focusing on that. So -3 comma 8, that's about here, and that's going to be an open circle. Amazing. Now we're going to check the other boundary. I like to have my boundary points. Why not? So we're going to plug in a 2. So this time, let's get rid of this and make that a 2 instead. So 2 squared is 4 minus 1, which is 3. And again, that's going to be an open circle. So 2 comma 3, make that an open circle here, and that's amazing. Now, technically, this actually is enough for us to graph our parabola as long as you're comfortable. It will look something like this. So you'll draw U right in here, but if that's freaking you out, we can actually just come up with a few more points. So for instance, I would find the Y values that correspond with -2, -1, 0, and then of course it's symmetric. But when we have our x coordinate of 0, we already know that y is -1, right? So 0 squared minus 1. We already knew that though. Let's find these other two. So -2 squared is 4 minus 1 is 3. And then -1 squared, that's going to be 1 minus 1, which is 0. So -2, 3. Perfect. Here's 1 point. -1, 0. Here's my next point. There's my vertex. And then, of course, it's symmetric about this vertex. So my next point is here. So I'm going to carefully, this might look a hot mess. Forgive me. I'm going to carefully draw this U. Sorry, it looks like crap. Whatever. It's fine. It's a U. Pretend it's beautiful, okay? It's gorgeous. Okay. For our last function, y is equal to -2x plus 4, our boundary is x is greater than or equal to 2. So I'm going to start with plugging in 2. So we have -2 times 2 plus 4. I'm just going to replace it. Why not? It's kind of helpful to see it. I don't mind drawing that in. X is 2. So -2 times 2 plus 4, that's a -4 plus 4, which is 0. Now, x is greater than or equal to 2. That is a closed circle on that endpoint, which is 2 comma 0. 2 comma 0 is here at the endpoint. And notice that if one's open, the others is closed. That's kind of how it works. Anyways, let's go ahead and pick one more point. We need an x coordinate that's greater than 2. It could be anything you want. So I'm actually going to go with 6 again because why not? Who cares? So I use -6. Now I'm going to use +6. So we have a -2 times a +6. So that's going to be -12 and then plus 4. -12 plus 4 is a -8. So 6 comma -8, that's about here. Beautiful. By the way, you didn't have to punch in any values. You know what the slope is. For the equation y is equal to -2x plus 4, the slope is -2. And if the slope is -2, that means fall 2, run 1. So check this out. From my point here to 0, I'm going to fall 2, run 1. And boop, fall 2, run 1. Fall 2, run 1. Fall 2, run 1. You see? It all works. It all works. Put it all together. Have fun with this. Really, truly master lines, parabolas, all that good stuff. And then, of course, all we have to do is connect them with an arrow, and you're done. Okay? No big deal. Don't overthink it. Break it up into parts. I hope this helps, and I will see you in class. Adios.